past the hour. The attendees have kind of leveled off, so I want to get started. Welcome everybody to the PIRE webinar series. My name is Feria Lozel. I'm a professor of astronomy and physics at the University of Arizona and a co-I of the Black Hole PIRE program. Welcome to the series on advanced data analysis techniques for the Event Horizon Telescope. Thank you for attending this series. And this is the fourth session. As we were just chatting over the chat, this is the second one on analyzing and understanding polarimetry techniques. All the webinars are available after the live webinar session on the Black Hole PIRE Science channel. So everything you have missed is going to be available there. Before we get started and before I introduce our illustrious speaker today, I just want to also let you know that we are supported by the National Science Foundation, and we try to bring you these educational opportunities as part of the Black Hole PIRE program. And one of the best ways in which you can help us keep on doing this is by providing your feedback to us at the end of this webinar through a very short survey. It just helps us make these webinars even better, adjust the level, adjust them to your needs, and come up with topics that are of interest to a wide variety of audiences. So just take a minute at the end, please, to give us your feedback so we can keep on bringing these webinars to you. With that, I am going to get started, introduce our speaker, Jason Dexter. Jason is an assistant professor at the University of Colorado, Boulder. He got his PhD at the University of Washington in Seattle. And prior to joining the faculty at the University of Colorado, he was a research group leader at the Max Planck Institute in Germany. He is an expert on accretion processes onto black holes, and his aims are to understand how they grow and how they help us test strong field general relativity. He has also worked a ton on polarization, which is the subject of our webinar today. And I think this webinar could not have been more timely given the release of the new EHD polarimetry papers, which Jason helped co-lead. So with that, I'm going to turn it over. We are going to take questions. You can put them in the chat or in the Q&A. If they are quick questions, I am going to facilitate them during the webinar. If they are more lengthy questions, I will ask to postpone them until the Q&A session at the end. So thank you, Jason. Please share your slides and get started.
Okay, well, thanks very much for the kind introduction and for the opportunity to present today. And thanks everyone who's here for coming. It's a pleasure to be able to talk about this subject, especially at an exciting moment. So the goal for today is that I'll talk about mostly the interpretation of polarized images from near black holes, similar to what's been done for jets for a long time, for example, with VLBI, but now going right next to the black hole to see what we can learn in particular about accretion physics, jet launching, and how black holes grow. Okay, so this talk is given on behalf of the Large Event Horizon Telescope collaboration, and I'll try to highlight people as we go, but especially I want to point out that a large number of postdocs and graduate students have made really important contributions to all of this science, and I think all of them. It's been a pleasure learning from them. And that would be the other point, is that my understanding of these topics continues to evolve, and so this is kind of a snapshot in time. I hope to continue learning as we do more of this exciting science. Okay, so the plan for today, we'll talk about kind of theoretical considerations about, say, polarized radiative transfer in a magnetized medium, and then go to images like shown here. This is the M87 image of ALMA that was also just released last week. And we'll talk today in particular at the end about the image from the Event Horizon Telescope down here and how we interpret this kind of swirling, twisty azimuthal pattern of magnetic fields. Okay, Great. So yeah, please feel free to chat or use the Q&A as we go along as well, since I don't know what level the audience is at. Great. Okay, so first of all, I believe this has been discussed before, but just as a little bit of background, we see the radiation that we see from low luminosity accretion flows in jets is synchrotron emission and inverse Compton radiation. And today we will focus on synchrotron emission. So shown here, for example, in a nice modeled SED of the galactic center black hole, Sag star, peaking near terahertz frequencies, or millimeter wavelengths, and similar type of spectral shapes seen here in a flux spectrum of M87. Okay, and so in both cases, we will focus on the region mostly near 1 millimeter today, and always in thinking about synchrotron radiation and its propagation through the magnetized plasma around these weakly accreting black holes. All right, and just quickly to note that the relative importance of these processes changes as you change the Eddington ratio of the source, of the accreting source, or the dimensionless unit, dimensionless m dot value scaled to the Eddington luminosity. So it's nicely shown here for a sequence of accretion models. There are also jet models that can explain the same radiation. And the basic idea is when we're at very, very, very sub-Eddington, like in the center of our galaxy, then we have relativistic electrons, high temperatures, which are this theta here, and low optical depth. And so we see the synchrotron peak very distinctly in this example, and then inverse Compton bumps of 1 and 2 scatterings. As you go to higher m dot, the cooling becomes more important. So the electron temperature goes down, the spacing of these peaks narrows, they come together, and the optical depth is higher so that you get more scattering. And so eventually, if you go up to, say, the hard state of X-ray binaries, for example, you would get something that's more like a hard power law here. And M87's spectrum in this type of model would be somewhere in the middle, just to give you a sense of parameter space. Okay, and again, we will focus on the synchrotron radiation and this initial peak over here. Great. Okay, so a schematic of how we calculate this. So the basic idea, those were the models from the last slide or the first slide were semi-analytic hydrodynamics solutions. So you put some gas around the black hole from whatever model. And then what we want to do today is calculate their polarized images. So we do this via ray tracing, where we put a camera at an observer, a distant observer's camera. We shoot rays backwards through our fluid volume and calculate along each ray, which corresponds to pixels on these images. We calculate the total intensity and the polarized intensity. And we will visualize linear polarization today as these tick marks in various forms. And so these are showing the orientation of the linear polarization, the electric vector position angle, EVPA, and the magnitude of the polarized flux is shown as the length of these vectors. Okay. And maybe just to briefly recap what we tend to see in these near horizon black hole images, and we get a bright spot where the gas is rotating towards us due to Doppler beaming, and this dark region in the center is the so-called shadow of the black hole here. Okay, great. So we can do this, as we said, from analytic models. Today, one of the main topics I'll focus on is using MHD accretion theory. And the reason for this is that if we do MHD simulations, we can actually study self-consistently the accretion process, at least for some numerical initial setup. So the basic idea here is that we actually generate accretion from an initial fluid distribution which is not accreting. Okay, so and that's due to for instance, the magnetorotational instability that causes turbulent stresses and accretion onto the center. So this is, for instance, a global simulation near a black hole here. This is axisymmetric in this case. The spin axis is pointing up, and this was a distribution of gas, log-scaled mass density of the gas. And you can see the turbulent fluctuations and that the gas didn't start out accreting and is now actually accreting onto the black hole. So these simulations are great because they let us realize a time-dependent, fully relativistic model of this near horizon emission in these polarized images. And they self-consistently evolve the magnetic fields and their turbulence, which produces the synchrotron radiation that we observe, the polarized synchrotron radiation that we observe. Okay, so going to the middle plot, then this is what the synchrotron emission looks like in the coordinate frame around the black hole. And then if we ray trace it, this isn't the same image, but it could look something like this right picture, where we can then include all relativistic effects and calculate what polarized images are expected to look like for some physical conditions around the black hole. Okay, so I'm going to talk at first about kind of what are the effects and briefly mathematically, here qualitatively, that we might expect to be important when we talk about polarized radiative transfer of synchrotron radiation near a black hole. So the first thing is that the synchrotron radiation is generally produced with very high linear polarization fraction, roughly 70% as a canonical number. And before we observe it, this polarized radiation then interacts with magnetized plasma, both in the source where it's being emitted and along the line of sight between the source and us observing it. And so effects then, what we need to take into account, or at least think about, are absorption, the self-absorption effect that goes along with synchrotron radiation, as well as the response of a magnetized plasma to polarized light. And the important effects there are Faraday rotation and conversion in a relativistic plasma. So this Faraday rotation effect may be familiar. This is if you start with a polarized light and pass it through a magnetic field, then its polarization direction will rotate by some amount, which depends on the density of the material, its field strength, and the length through the so-called screen, here the blue cylinder from Wikipedia. Okay, and it turns out, I'll argue in a second, this is really an important effect, Faraday rotation, so we'll talk about it a lot today. Okay. Great, so I want to briefly just show the polarized radiative transfer equation written along rays. So again, on light rays, from our camera to a black hole, and that can account for example, light bending and those types of effects. But this is a non-relativistic version of this written for the 4 Stokes parameters, intensities on the left. And then the way to read this in words is that we have a change in intensity along our path. We add to our ray due to emission. We subtract from it due to absorption or Faraday effects, these alpha or rho coefficients here for each associated with each Stokes parameter. And that modification modifies our current intensity. So multiplied again by this. And you can see that the units of these different quantities here in case you're curious. Okay. So this is how these terms are encoded. I think that the key thing to realize right away is that the diagonal terms are purely absorption in Stokes I, and this is what you typically think of in radiative transfer as absorption along a light ray. And these Faraday rotation or other sort of birefringent effects that depend on the polarization state of the light are purely off-diagonal terms in this matrix. Okay, so that'll come back in a second. All right, and the other thing to notice right away is that this is a first order linear set of ordinary differential equations along our path length, which we've parameterized as some distance s here. And the only tricky thing about solving these equations numerically is that they're so-called stiff equations, meaning that once I hit the so-called optically thick regime, where the term on the right-hand side becomes important, then suddenly the nature of the solutions changes. And that makes it somewhat difficult to do these numerically in regions of high so-called optical or Faraday depth that we'll define in a second. Okay, and I'm showing here the relativistic version. And I just want to make the point that these are actually only slight modifications to the basic equations that do not change the nature of the equations. But this is one way to write down a formalism for solving these equations that accounts for Doppler shifts and redshifts. So using invariant forms of the different J, the emissivities here, and K, this matrix here. Okay, and this also allows you to take into account the geometry, parallel transport, as well as just the geometry of a changing magnetic field direction along the line of sight. But there are lots of ways to do this. This is just one way to write this down, and I just want to make the point that this doesn't change the basic nature of the equations that we solve. Okay, so a couple examples. Just to give you an idea of these, this may be familiar from radiative transfer. This is just pure absorption, a toy model example of Stokes I and Q. So Q and U are related to linear polarization, while Stokes V is related to circular polarization. Okay, and so here we can define a characteristic scale over which we get an exponentially attenuated contribution to our intensity. So for example, if you look at this curve, it's flattening out. And this just means that we're getting to a region of higher optical depth, where even though we're continuing to emit, we're no longer adding to our intensity. And we can determine that scale related to the path length times the absorption coefficient. And this is what's called the optical depth. For instance, what sets the photosphere of an object, a star or some other radiating object. Okay, What maybe is less familiar is a solution of pure Faraday effects, pure off-diagonal terms. And here we can define an analogous quantity, the Faraday depth, but the nature of the solutions is qualitatively different. So here we have oscillatory solutions for our intensities and the oscillation frequency is dependent on the coefficients rho, the Faraday coefficients rho. Okay, and so we're going to call this in this talk the Faraday depth, the scale at which Faraday rotation becomes important and rotates the EVPA vector around. Okay, and I just want to note there are many people who've developed codes for these. I've listed just a few examples there. And within the EHD, we're doing a code comparison project that's ongoing, led by Ben Prather in Illinois, graduate student in Illinois. Okay. Great. Okay, so the next thing is that I just want to give a qualitative argument to back up what we're going to find, which is that in theoretical models of both the galactic center black hole, Sagittarius star, and M87 at 230 gigahertz, we tend to be in a regime where these Faraday effects are kind of important. And so one way to write this is that our Faraday depth over here is proportional to the density, the magnetic field strength, and the size of the emitting region. It goes like nu to the observing frequency to the -2, or lambda squared. And it has this temperature correction when you're in a relativistic plasma that tends to reduce the strength of the effect. Okay, but maybe one key thing to see here is that if you're at high frequency, this effect falls off as a power law in frequency, whereas absorption has an exponential type decay with frequency. And so if you plot the ratio of those two effects that we showed on the last slide for these qualitative solutions of oscillatory or exponential type solutions, then if you're at high frequency, the Faraday effects become more important if you're sort of mildly relativistic. So like say the blue curve or red curve here, this ratio of the strength of those coefficients becomes larger than 1, and it can even be as large as say 100 here. Okay, and so this is just to motivate, and we actually think that we're somewhere in this regime in Sagittarius star and M87. We may well be in this regime, high frequency, even though and moderately relativistic. And here you can calculate what might be the Faraday depth for some. I'm trying to write this in a way which is source agnostic over here. But if your relativistic temperature, KT over MC squared, is about 10, and this is a plasma beta, the ratio of gas pressure to magnetic pressure, then at 1.3 millimeters or 230 gigahertz where the EHT observes, this Faraday depth can be large. Okay. So there's an analytic argument to back up what our numerical results is, which is that we often find, if we just solve the equations that we showed, that the Faraday rotation effect is really a critical one in studying the polarized radiation. It tends to change the nature of the polarization in a lot of the theoretical calculations that we do. Okay, so the other key point on Faraday rotation is that there are at least two distinct regimes of what can happen when Faraday rotation becomes important, meaning when this Faraday depth becomes larger than 1 or pi or 2 pi or so. So there are two things. One of them is a classic technique that's used in astronomy, say to measure magnetic fields along the line of sight, which is what we call external Faraday rotation, which means like the Wikipedia cartoon, imagine that we have a polarized point source and that all light rays coming from that point source undergo the same rotation of their EVPA. Okay, then if we measure, this effect goes like lambda squared. And so if we measure then the EVPA at two different wavelengths, we can measure what's called the Faraday rotation measure, RM, usually expressed in these weird units of radians per meter squared. And if we're in this purely external model, then our Faraday depth is related to our RM measurement like this. And that means that we can measure properties of this cylinder, this so-called screen, which is causing the Faraday rotation along the line of sight. Okay, in external rotation. This does not depolarize on the left. It does not change the degree of the polarization of the light. It just rotates it. And if it rotates it coherently across the source, there will be no depolarization in the end. Okay, for accretion flows, there's another effect which is important, which is that different lines of sight, if you picture on the camera, different lines of sight can be passing through a slightly different magnetized medium. And if the Faraday depth is large, then the fluctuations in the Faraday depth between different lines of sight may also be large. And now you can get different amounts of rotation or even depolarization along each ray. And so that's what's shown in the sample polarization maps here. One of them where on the top where Faraday rotation is not important, and one of them on the bottom where Faraday rotation becomes important and ends up scrambling this nice polarization pattern here and modifying it from what you would have otherwise seen without that propagation effect. Okay, so maybe it'd be useful to go over examples of how this has been used for studying the galactic center, where these techniques are a very powerful diagnostic of accretion physics. So the idea of the external Faraday rotation measure is motivated for the galactic center because if you measure the EVPA shown in relative terms in a plot from more recent ALMA data on the top right, then you can see that at 4 different wavelengths plotted as wavelengths squared here, that this is that you see a straight line provides a good fit to these data points, meaning that this would be the external RM model where the EVPA goes like wavelength squared. Again, the 3 lines are 3 different epochs, showing that even though you have some time variations in Sagittarius star, it always seems to be following this wavelength squared behavior, as far as we can tell on sort of average on longish timescales, a day. Okay, and so what you can do then is if you imagine that what's happening here is a model developed by Dan Moroni et al., then maybe what's happening here is that you have a polarized point source near the black hole that's radiating, and then this green, fuzzy green stuff is an ambient accretion flow falling onto the central source. And so your Faraday rotation measure, written as an integral here, this is related to this coefficient, the form of this coefficient rho v in the non-relativistic limit. You can write down what this Faraday rotation measure should be once you integrate through the source. And you can turn that around then knowing radial profiles of density and magnetic field strength from accretion theory. You can turn this around and phrase it, for example, as a way to estimate the accretion rate onto the black hole, m dot, the accretion rate. And so here, one particular solution for that is shown here from some inner radius where you're assuming the electrons become cold, basically. But this will give you a range. This was used to derive a range of 10 to the minus 9 to 10 to the minus 7 solar masses per year for the accretion rate onto the black hole in the galactic center, which is very interesting because that's significantly lower than what's available at the Bondi radius on much larger scales. This is a really important results in accretion theory that we can get from Faraday rotation studies. Okay, the other case of internal Faraday rotation is also very useful for the galactic center. So this actually came before the discovery of the Faraday rotation. And the argument here is that there was a discovery published in Aitken et al. 2000 that there's a 5 to 10% net linear polarization fraction, so integrated over the source, 5 to 10% linear polarization seen from Sagittarius star. And the argument was basically, okay, it's polarized at 230 gigahertz, so we can't have an enormous Faraday depth because by the internal Faraday rotation effect that within the source that's radiating, because as we discussed, that should depolarize the emission. And so then to avoid depolarization, we should have something like tau rho v less than 2 pi, meaning that an individual light ray doesn't go around more than, say, once. And this is just to avoid too much cancellation or depolarization. So that's a very order of magnitude type estimate, but it's extremely important for the galactic center because this again meant that we must have then relativistic electrons radiating, a low accretion rate, much lower than the Bondi accretion rate available at large radius. Okay, and if you, just to give a sense of how useful this is, if you use the brightness temperature measured from radio images of the galactic center, and here it's to order of magnitude, say it's somewhere in the range several times 10 to the 10 or 10 to the 11, then you can actually use this to estimate, say, a particle density or a magnetic field strength near the black hole. And so this was done immediately following this discovery, considering constraints on plasma properties from just the presence of linear polarization. Okay, and there are a lot of interesting twists on this. One of them is that to get this to work, you have to assume that there are coldish electrons around at these temperatures. So the solutions can actually qualitatively change as you go to very high temperatures. But as long as there are some coldish electrons around, these constraints hold and provide useful constraints. Okay, great. So that was one thing. One takeaway point should be that the Faraday rotation effect for accretion flows is actually very important for low luminosity accretion flows for say estimating m dot or constraining the parameters of the emission region, say the density or magnetic field strength. Okay, and the last thing here, just to show this is a really nice density profile going from, in units here of the Schwarzschild radius, from the Bondi radius at about 10 to the 5 on here, down to the black hole. And this is a density, particle density. And all the different regions, shaded regions or points on here are different observational constraints. And the only point I really wanted to make about this is 2 of the key constraints come from the polarization measurements that we just discussed. So it's schematically shown here, but the Faraday rotation measure constrains things at scales of, say, 100 Schwarzschild radii or so, 10s to 100s. And the one that we just discussed right next to the black hole in the emission region itself would be shown schematically here as this number 2. So we learn a lot of really important information, and of course even more when then combining it with other observations like X-ray observations or total intensity observations. Okay. So Faraday rotation is a really important diagnostic of accretion flows and helps us to measure plasma parameters. Okay, so when we go to images, as we will a little bit in this talk, we can see the effects, as we showed already, that if you're sort of at low m dot and high temperature to produce the same emitted flux, then you end up with, say, an ordered polarization map. Whereas if you go to higher m dot and lower temperature, then you can get this Faraday rotation and this scrambling. Whoops, sorry, it went the wrong way. And so when we think about resolved images, we can do this a little bit better than what was possible with just a single measurement of a polarization fraction. And we can show that actually, if you think about imaging this, you're sort of, one way to think about this is blurring the polarization map here with a beam. And what happens when you scramble things in the bottom left panel there is you'll tend to reduce the average fractional polarization seen at the scale of your beam. And this is a really nice plot made by Alejandro Jimenez Rosales, postdoc in Nijmegen, showing that at low tau rho v, you get very high average fractional polarizations on an image. This would be like the top left case, 60%, not that different than what you emitted. But if you go to very high tau rho v, you get a lot of this scrambling, and it depolarizes your image at the scale of a beam. So this is very important. This will come back later when we think about the Event Horizon Telescope images of M87. Okay, the next basic thing that we would like to do with polarized light is we would like to study magnetic field geometries right next to a black hole on event horizon scales. And the way this works is that the polarized synchrotron radiation is emitted perpendicular to the wave vector, to the line of sight, and to the magnetic field direction. And so if we can map out the EVPAs, we can then in turn, that will depend on the magnetic fields that are near the black hole. And we can learn about what magnetic fields are doing near black holes, which is a really important type of measurement to make, since those are the magnetic fields which are launching jets and are allowing the gas to accrete on sort of the scales where energy is released right next to the black hole. So what's shown here are idealized magnetic field configurations, toroidal, radial, and vertical magnetic fields, and there are sort of schematic pictures of what the field lines would look like down below. And we're just going to try to understand these maps of why do the EVPA structures look how they do in these different cases. And this basically amounts to doing cross products, K cross B. Okay, so let's look at the toroidal case first. So this diagram down below shows the magnetic field direction looking nearly straight down. These are at the geometry of M87, so looking nearly straight down the jet for M87. And so here, if we look at a purely toroidal magnetic field, then the line of sight is nearly out of the screen. And so if we do K cross B, we'll get a polarization pattern, which is just purely radial. So the EVPA pattern will be purely radial for the toroidal magnetic field case here. Okay, and we can look at the other ones then. For radial magnetic fields, it'll be the same as we just got, but all of it rotated by 90 degrees. Shown here. And the vertical field case is a lot more interesting. If you just did K cross B with no relativistic effects, you would get something pretty close to 0 and purely vertical in this plot everywhere. But actually, when you account for relativistic effects of light bending and aberration, you end up with an interesting kind of twisty pattern. Again, I'm not going to describe that in more detail, but just kind of an interesting result. And I would also highlight, as well as the EHT papers going over this, an upcoming Narayan et al. Paper that develops a really nice analytic model for understanding these K cross B type calculations. Okay. Great. Okay, and the only other thing I would point out is that the toroidal magnetic field case or radial, but focus on the toroidal, if you were to go around this once, you would twice see both linear polarization vertical and horizontal in one oscillation. So that'll become important in a second. Okay, great. And the reason that we care about direction, it'd be interesting to map out magnetic field geometry around a black hole anyways, but the reason that we're particularly interested in this is because in a rotating fluid, we will tend to drag an initially weak magnetic field along with the gas, and it will end up in a toroidal configuration. The toroidal field component gets amplified as well, and so we'll end up with a toroidal magnetic field near the black hole if the magnetic fields that are brought in from large scales with the gas start out weak. Okay, and so if we see something else other than toroidal, then that means that we managed to accumulate a strong magnetic field, meaning that it can resist the rotation of the gas and can remain pointing with some component pointing in another direction. And that's only important if the magnetic fields near the black hole are actually dynamically important. They can push back on the gas. So we call these strong magnetic fields. And an extreme example, a cartoon of an extreme example is shown on the right, where imagine that you have a black hole magnetosphere, which is pointing, say, vertically in that case, and manage to actually disrupt the accretion flow onto the black hole. Again, another example from astrophysics would be around a neutron star. If you have a strong enough dipole field, that can actually modify the flow of gas strongly and collimate it along magnetic field lines. Okay, so not only from the EVPA pattern can we get at magnetic field directions, but that also encodes the strength. And so we can learn about, are these magnetic fields near the black hole dynamically important? Okay, so I'm going to give one example before we do the M87 image. This is an example not from imaging, but in a way from spatially resolved observations of polarization near a black hole. So this is with infrared interferometry. The advantage here is that we don't have to worry about Faraday effects because this is even higher frequency, but the downside is we don't have imaging. But what we've seen with the gravity collaboration results in infrared interferometry done in PIRE, Chile, is that for 3 flares, you see a clockwise rotation of emission of transiently accelerated electrons near the galactic center black hole. So shown over 30 minutes going from the red to the yellow and green around to the blue. And the motions that we see are at a scale of tens of microarcseconds, which corresponds to 3 to 5 Schwarzschild radii in radius. And the apparent speed then on the sky is something like 20 or 30% of the speed of light. Okay, and so this rotation was seen in 3 flares from 2018. And for the purposes of today, the important part about this is that we see polarization angle evolution at the same time. So we can try to use these observations to get at the magnetic field orientation and strength around the galactic center black hole. Okay, so the way that we picture this working, some compact region, a so-called hotspot of accelerated electrons, for example, which is then evolving in time, going around, in this case, this way. And the idea then is that when the emission region is in different locations, it's sampling different parts of our EVPA map. And so it's tracing out the magnetic field structure in time. Okay, and so what we find there is that, again, you would expect to have, if you go around once, you should have 2 oscillations of the polarization angle. You see both vertical and horizontal linear polarization twice. And what we see instead, these are data from a different flare, total intensity shown here, and the polarization angle here in orange. And this corresponds to a astrometry where the emission region rotated around once. And the polarization angle goes around once as well. Okay, and it turns out that to do that, we cannot have our toroidal field map in this model. And so that would require some strong poloidal component, vertical or radial component mixed with toroidal to get the observed pattern. Okay, so this is at least implies that there may be dynamically important magnetic fields on horizon scales around the galactic center black hole. Okay, So last, but certainly not least for today, I want to talk about the new, as of last week, M87 EHT polarized images in linear polarization. And again, I have the great fortune of presenting this work today, but a lot of people did, in the collaboration of 300 or so people, did a huge amount of work on this, on going to telescopes, developing instrumentation, developing algorithms, doing many other things. And so I've listed here specifically the members of the paper writing teams for the two papers that came out. But these are huge collaboration efforts. And so I just want to, everybody should get the credit for these results, not just those of us who are fortunate enough to get to talk about them. Okay, so the image is shown, the polarized image is shown for April 11th here. The grayscale is the familiar, maybe glowing ring image of M87 from the Event Horizon Telescope before. And now we've added these EVPA ticks on here, which in this representation are color-coded with their fractional polarization. Okay, so I will talk a little bit about the data following up on Yvonne's really nice webinar last week, but refer to that for more details since I'm more focused today on the interpretation. Okay, so I think a couple of punchlines from the huge technical achievement of making these polarized images. A couple things is that we have many different methods for reconstructing polarimetric images, regularized maximum likelihood methods, sort of clean-based methods commonly used throughout astronomy, and then even Bayesian fitting methods to try to fit for the polarization at each pixel. And the point would be that all these methods find consistent results. This is one example from that day, April 11th, of images from different methods. And the other thing is that if we average images taken from across methods, then we can look at on each day. We have a pretty consistent result on each day with some minor changes in, say, EVPA. So these are 4 different days. I'm represented as our tick plots here, and then these field line swirl plots down below. Okay, so I just want to emphasize that this was really a tremendous amount of work to get to these results, and all the people who worked on the analysis, the data, and so on. Polarimetric calibration, these D terms that Yvonne talked about last time, is a tremendous amount of effort and a great technical achievement. The EHT is a great facility, but it's made up of many different facilities. And when you do this polarimetric calibration, you have to worry about each telescope individually as well as them as a collective whole. And so it's a really impressive achievement coming to these results. Okay, so from an interpretation point of view, based on what we've discussed so far today, the things that really jump out when you look at this, at least to me, when I look at this polarized image, is that we see this sort of twisting or azimuthal type EVPA pattern shown here, like sort of spiraling with the ring. And the linear polarization fraction at our resolution, which is about 20 microarcseconds, here's the 50 for comparison, is about 10%. So these greenish or bluish colors and not reddish colors in our color bar are much higher. So this is way, way lower than the 50 or 70% that you might have expected at this scale, and suggests that something is depolarizing the emission. Okay. So before I talk about the results, I just want to say the other thing that is done from the data is that basically based on those, what we think are the critical things to measure, the different methods can be used over different days to define ranges of parameters that we can use to compare to theoretical models. So these are shown here. The different ranges are from different methods, and we just take the sort of the range of all those methods and across a couple different days. Okay, and those observables then are the net linear polarization fraction integrated over our image. This has been measured before from M87 to be about 1%. We find that it could be somewhat higher than that. And then this average linear polarization fraction, which is an imaging result. This is the average on those ticks on the image, and it's something around 10% or a little bit lower. Okay, and the other key thing is that we showed before that the EVPA structure may be telling us really important information about magnetic fields. So we want to quantify that. So we can quantify that through an azimuthal decomposition on the image. which actually, interestingly, for those interested, please refer to the papers. But this is actually related to an E and B mode type method that one can do also on the data. But this is an azimuthal decomposition, which tells you how those EVPA ticks are distributed over the ring image. Okay, so we have an amplitude. This is a complex quantity that has an amplitude and a phase. So the amplitude tells you sort of how much power is in that, how much polarized flux is in that mode, or fractional polarization is in that mode, and the phase tells you how the EVPA structure is oriented. Okay, so we can measure these quantities for comparison for interpretation purposes. So the one I want to highlight is this azimuthal decomposition, which is really important and really nicely, this one particular mode we call beta 2, or dubbed beta 2 by Palumbo, Wong, and Prather, 3 graduate students in the EHT who developed this method. It's really nice because it maps onto the idealized magnetic field structure models that we discussed before. So I don't want to belabor exact values or anything, but the phase of this beta 2 can tell you basically the difference between how your toroidal B structure, so radial EVPA, your radial B structure, azimuthal PA, has a certain value. And the vertical case doesn't map perfectly onto this mode, but it's not actually bad. It's sort of somewhere over here. Okay, so this is a really important development for our interpretation, because it lets us quantify the pattern that we observe and compare it to what we get from theory. Okay, and then the basic, again, the qualitative case is that if we ignore for a second in Faraday rotation, which I've told you is important, and we'll return to that, but if we ignore that for a second, then basically we can say, well, we don't see this pattern over here in the top left. We don't see the radial EVPA pattern corresponding to a toroidal magnetic field, and that suggests at least that we may have the presence of some poloidal component of strong magnetic fields near the event horizon in M87, some radial or vertical magnetic field component that stays important. Okay. So that would be qualitative result number 1. The other thing is that we discussed earlier the importance of Faraday rotation, and I just want to show that here in some theoretical models that we use to interpret the data that I'll explain more in a minute. But basically, the statement would be that we observe this 10% average polarization at the EHT resolution, and we interpret that as being the result of Faraday rotation, this internal Faraday rotation effect, which then can scramble the intrinsic pattern. So in these images here, we're showing no blurring. The native resolution of calculating the images is in the left column, and then blurring it. So I'd focus on the right column, this 20 microarc seconds. And the top row is when we do the full polarized radiative transfer calculation with all the coefficients like we showed at the beginning of the talk. And the bottom row is when we ignore the Faraday rotation effect. So we just set rho v equals 0 and do the same calculation. And what you can see is if you look in the left column, the tick marks are much more ordered. They're much more coherent in this bottom left panel than in the top left panel. And that means that when we go to blur the images, we depolarize. This is beam depolarization, and we're smearing out different directions and canceling the polarization. And so this effect can really nicely explain the depolarization that we get at the EHT scale. And as far as we're concerned, it's a much more natural candidate for producing the low polarization we see than, say, very tangled magnetic fields due to turbulence. At least in simulations that we know how to do, we don't know how to make turbulence that produce that much depolarization. And we also don't think that the absorption effect is very important near M87. So we don't think that it's self-absorption. One really nice thing that we are not officially interpreting, but one thing that I think is very interesting is that if you look at this spot up over here, it starts out in the version, it's similarly polarized in the version with no Faraday rotation. And then it actually becomes significantly more depolarized when we turn that on. And so I'm not lining them up one to one, but there's an interesting argument that there's part of our ring in M87, this part of the ring is more polarized. So it'll be interesting to watch in the future if that persists or if that goes away. That basically Faraday rotation would be one explanation for getting part of your ring to be preferentially depolarized, just because the Faraday depth is higher there. Okay, so that would be the other qualitative result is that we think this is an indication that Faraday rotation is actually playing an important role in modifying the polarization that we see, helping to depolarize it down from, say, 50% polarized to something more like 10% that we observe with the EHT. Great. And so what we can do with that, so this is a qualitative result number 2. Number 1 would be taken at face value. We don't seem to have a toroidal magnetic field, and so the fields appear like they could be dynamically important next to the black hole. Number 2 is that we can use a one-zone model, very similar to what we discussed earlier for the galactic center. And we can impose constraints related to the brightness temperature of the source as a lower bound on the electron temperature that we need to produce the total flux density at 230 gigahertz that we observed from M87. And now the new constraint here would be that we think Faraday depth is kind of important. And so let's require it to be larger than some value, which we pick here as 2 pi, meaning that Faraday effects are capable of rotating the polarization around. And if we impose those constraints, then the one-zone model result is shown in the plot here. The different color contours are different constraints that were optically thin, that were Faraday thick is over here, and so and then we produce the right flux. And so for any way of picking one parameter, you can get some allowed parameter space here. Right? It's not as narrow as shown here because there's another whole dimension. But from this, over a wider range of parameters, we can then again estimate what are the plasma properties right next to the black hole. And so in particular, we infer one interesting quantity you might be curious about is what is the magnetic field strength in Gauss. And so we would say that that's roughly 1 to 30 Gauss next to the black hole. And similarly, the electron temperature, we would say can't be too high. Otherwise, you would suppress this Faraday effect. And so we think the electrons must be, still relativistic, but moderately relativistic, not say ultra relativistic next to the black hole. Okay, so qualitative result number 2. So you may have noticed these qualitative results are I think, great. They're very informative and end up being consistent with what we think is the full picture. But I would just note that they're also sort of in tension with each other, right? We just said that we think Faraday rotation is probably pretty important. That causes oscillations in the EVPA. And yet we're reading off the EVPA at the same time and saying that, aha, that tells us that there's dynamically important magnetic fields, strong magnetic fields. So what we did to try to deal with this is we turned to numerical simulations where we can include all these effects. They're limited in parameter space coverage, in other unknown things. We don't claim to be able to make the only possible models, but we at least then have a way to realize the combined effects of Faraday rotation with turbulent magnetic fields, relativistic effects, and all those things in one physically self-consistent picture. And so we use those to help us understand the M87 polarized images. Okay, so this was a gallery of some of the images generated for this effort within the EHT and led by members of the Black Hole PIRE group in Illinois, are shown in these animating polarization maps down in the bottom at their native calculated resolution, and then also blurred how we compare them to the data. And so all in all, we calculated 72,000 such polarized images, and we're able to span parameter spaces of weakly magnetized accretion disks, or relatively weaker accretion disks, which we call sane, and these magnetically arrested disk configurations, which are the strongly magnetized disks that we know how to make around black holes. We also can vary then properties of the electrons, which are not specified already in the simulation, and we can do these across a range of black hole spin, including retrograde spin models, which hasn't been done much before. Okay, and the radiative transfer code used in this case is one developed by Monika Mostrzebatska in Nijmegen. Okay, so I should say, so what we do quantitatively is we then have a couple different ways to compare quantitatively the observables that we talked about before, the net polarization integrated over the image, the average polarization at the scale of the EHT beam, and things related to the azimuthal decomposition, its amplitude, and then also the part that's encoding the EVPA structure around the ring, taking the data ranges that we defined earlier. And so I just want to show there, if we require all these constraints to be met simultaneously, then very few of the actual images we have are deemed passing. So there are a lot more here in the bottom row that don't work than in the top row that work. I just want to show that even though we don't actually choose things to look like the EHT image, we use these kind of average diagnostics, we end up with things which are not such a bad match. So these top couple examples here are at least sort of show great resemblance to the actual observed M87 image down here. And the ones that fail tend to be way too polarized. This is a model where you can see the toroidal field structure here, the radial EVPA pattern and very high polarization fraction, or like in the bottom right where the image is almost completely depolarized by Faraday rotation. Okay, and so we can quantify this and basically just ask if we collapse things down to sets of models, what are the things that do the best? We have two different methods to do this. One of them is applying all the constraints simultaneously on the left, and one of them is more of a joint approach of just requiring that one image, that at least each constraint is met by at least one image taken from a time series from that model. But in both cases, I just want to say that as far as we are able to tell, we generically favor the strongly magnetized scenarios for accretion onto M87. Okay, so that we get larger numbers of images or larger relative likelihoods on the right side of these two plots than on the left. And this nicely matches the qualitative conclusions that we had earlier about dynamically important magnetic fields from this twisting type EVPA pattern. And similarly, we can measure then what are the physical properties near the black hole from the passing models here. And they agree very nicely actually with our one zone constraints that we arrived at earlier. Okay, so I just want to go one step further and say that if you're on board with this comparison of numerical models with the image, then you can also try to estimate other properties of M87. So we can estimate, say, the mass accretion rate. So on these plots, the blue is what we had from the total intensity comparison of the ring image with the data. And the red is now our restricted parameter space from polarimetry. And the key I want to get across is just like we said earlier in the talk, polarimetry is really good at measuring physical properties of accretion flows. And so in this case, we can estimate now the accretion rate onto M87 and argue that we think it's probably lower by a significant amount, about a factor of 100 than the Bondi accretion rate. So actually not that different of a scenario than the Galactic Center in that way. Okay, and one thing, there's a lot of interesting future work or things that should be done. It's an exciting time for this. I just want to mention one, which is that the jet power that we get from the models that we have that work, still it spans the full range that we have available, but it's still sort of towards the low end of what is measured on larger scales from M87's jet. So there's still possibly an interesting issue to study more there. Okay, great. So to summarize what we talked about today, the polarization direction and degree depend on magnetized plasma properties. In the case of accretion flows, these provide really important constraints on how much mass is accreting, how hot are the electrons. And also, now that we can image polarization patterns, that we can actually measure both the strength and the structure of magnetic fields right near black hole event horizons where jets are launched and where accretion energy is being released. And then we talked about the resolved EHT image of M87, and that we interpret the relatively low polarization, this 10% polarization at the EHT scale, as a constraint on electron temperature due to Faraday rotation. And we can also then constrain the accretion rate, as we mentioned. And this twisting EVPA pattern suggests that there are dynamically important magnetic fields near the event horizon of M87, which is really interesting input for models of, say, launching its relativistic jet across scales of the galaxy. Okay, and I would just add one more time that to me, this is the beginning of a story, or maybe the early part of the middle, and definitely not close to the end. And there'll be continuing observations, the Event Horizon Telescope, and I really look forward to learning more about this topic in the future. Okay, so thanks a lot for your attention. And yeah, the last thing, the link there is to this survey. So before you leave, please do that. But for now, I'm happy to take questions. Thank you very much for your attention.
Thank you so much, Jason, for walking us through how polarization is generated, how it gets scrambled, and what it means for the EHT images. Very nice webinar. I just want to remind everybody that you can ask your questions either through the Q&A feature or through the chat feature, and I can moderate them, and Jason will be happy to answer questions for at least 5 more minutes. Right now, there are no open questions. There is a raised hand. Okay. Yifan, would you like to type in your question, or I can try to allow you to talk? Apologies, that is not working right this second. Can somebody allow Yifan to talk?
I can. I think I can talk now.
Oh, okay, wonderful.
Okay. Thank you very much for your very nice talk. So my question is, I can understand for the direct emission, this EVPA is related to the the transfers to the projection of the B field. But what about for the length photons? I think on the ring they contribute like quite a lot. Do they have the same direction, or will they like wash out or give some turbulence?
Yeah, thanks. It's a great question. So we think about the direct emission, meaning the light can still be bent, and light bending effects can play an important role. Like in the vertical magnetic field case that we showed, they play a very important role to producing a swirling pattern. For the photons that go around the black hole one or more times, that we think that those contribute something of the order of 10% or maybe up to 20% of the total flux. So they're a subdominant component. There's also some really interesting work about how polarization patterns on that photon ring actually encode relativistic properties because of how they're modified. We also find in the simulations that this 10 or 20% of the light tends to be relatively depolarized with respect to the rest of it. So I would basically say that's a really interesting question. At first glance, I would say that what you're seeing mostly is the direct emission, and that will depend on the magnetic field structure. But yes, you would in general expect different polarization properties for the photons that actually go around one or more times. And that there's a lot of interesting recent work on that I did not discuss today.
Okay, thank you.
Jason, there are a couple of questions in the chat. You already touched upon this a little bit, but can you explain some more? How do the general relativistic effects matter here?
Yeah, it's a good question. So yeah, I think the main effects that we have are due to the aberration and the light bending. So we have a parallel transport effect, which can also rotate the EVPA a little bit. I think that currently, I'm not sure I have a great answer on. They really matter for shaping the images in general, right? So I think within that scheme, they don't seem to produce large extra changes to the polarization pattern, except as I mentioned in the case of, say, if you were to put in by hand a purely vertical magnetic field. That result may also depend on inclination. To some degree, viewing M87 at lower inclination probably reduces the changes from parallel transport as well, since the largest amount of the light bending would be at higher inclination would be when you look behind the black hole, for example. So, I mean, it's impossible to say they don't matter. They have a huge impact on the images, and we see the polarized image. But I think for this kind of K cross B logic, I think in a lot of the models with toroidal and radial fields, they don't make such a big difference in the EVPA pattern that you see.
We have a question from Maciek Wilgus.
Yeah, I see the Maciek question. Sorry, I can.
Yes.
You don't have to read it.
Okay.
Yeah, it's a good question. So right. Okay, I've actually worried about this a fair amount for Faraday rotation coefficients. Yeah, so all of these in the radiative transfer, the way that we do it, we want to be able to calculate things fairly quickly, and so we use fitting formulae. So approximations to the full integration of the single particle effects over the distribution function. And so these have been calculated in different limits. The plot I showed in the beginning was Jones and Hardy 1979, which is the first I know for, well, I probably shouldn't say first. I was supposed to never say that word. Maybe one of the first ones for Faraday rotation in a thermal plasma. But I think there are lots of different different work on this. So their fitting formulae, they have some error associated with them, but I would be surprised if it's large. And I think one of the key things when you do these calculations is for the Faraday rotation is you need to make sure that the cold electron limit, where there's no temperature dependence, you need to make sure that that limit is reproduced accurately. I would say that's probably the most important thing. How well are they known? They all okay. And I would just advertise again. Ben Prather is leading this code comparison effort, and one of the things that we've looked at is different fitting formulae, specifically for Faraday rotation, because I think that is the most important. But also for the other coefficients will be tested as part of that effort.
So the next question is, you showed that the magnetic fields around M87 are around 1 to 30 Gauss, but neutron stars can have as high as 10 to the 15 Gauss. Can you explain the differences between them?
Yeah, neutron stars are small. They're also really highly magnetized, so don't get me wrong. But actually, one interesting, tidbit that I learned in this is that apparently M87's magnetic fields in Gauss are not much stronger than the Earth's. And I think the main way to understand that is that densities are also very different. So we showed the particle density, as far as we can tell, in the gas around M87 in the emitting region is 10 to the 4, 10 to the 5 per cc. And that is an enormously low density. That is an incredibly low density in that region. So when thinking about physical values of magnetic fields, I think the really important thing is to compare it with something. So compare it to a mass density, for example, b squared over rho, a relative amount of energy contained in the magnetic field per mass, or to a pressure to say, are the magnetic fields strong in the sense of being able to push the gas around? So in Gauss, I agree, the magnetic fields near M87 are tiny, or modest. But in terms of the important thing when we say strong magnetic fields is, can they influence how the gas moves? And that's better done by comparing, say, the magnetic pressure to that of the gas, for example. Yeah, the basic effect here is that it's the volumes are huge and the densities are low, and that reduces greatly the magnetic field strength in Gauss.
Thank you for that. Let's take one from the Q&A. This question is asking, in the animated pictures of the Sagittarius star spectrum, I'm not sure if they mean spectrum, but why were there some rotating clockwise and others counterclockwise? I'm wondering if this means
the gravity results, maybe. Do you think?
Maybe the gravity results.
So I think in the gravity result we showed a cartoon model which is rotating the wrong way compared to the data. So I don't know if this is getting at the question, but I would say the key thing for understanding how that gets at polarization near black holes is that we're assuming that we see that there is a rotating emission region, and we're assuming that is sampling magnetic fields in different regions around the black hole. So that what you see in time would be measuring something about the spatial distribution of the magnetic field. And on the sky, it's clockwise, which is the important one. And when we compare models and data, we do that in the right direction. So I hope that answered the question.
I hope so too. We have a question from Mark Reed. Do the models or observations constrain proton-electron versus positron-electron plasma?
Yeah, so everything that I talked about here would be proton-electron. But I would say that I think this is correct, that I don't think any of the qualitative discussion was strongly hinging on that. I do think that solutions for circular polarization in particular definitely depend on positron-electron plasma, and so in that, as much as we talked about that today, then we'd be assuming proton-electron here, which is a good assumption if everything we're talking about is related to inflow, or probably to what happens at a jet wall. I think the only way that those conclusions could be modified is mostly for circular polarization, but also for interior of a jet funnel, if you're able to produce pairs there, for example, and see the radiation from those. We think the pair production rate is pretty small and that's not an important effect for M87, and that it won't produce a lot of emission at our frequency for sure. But there are studies of positron-electron polarization. So Richard and Antua has a recent paper about this. I was focusing more on today we're focusing more on the proton electron case.
Let's take just a couple more questions. This one is, does the relativistic aberration and corresponding UVPA rotation vary strongly across the HD polarization image based on the modeling work?
Yeah, so I would say that we don't. So those effects are included in calculations. So I understand your question. I guess what I would say is that I don't immediately know how to disentangle. I don't know what observational handle we have on aberration directly, because even if, forget the Faraday effects or other complicating effects, we don't know the magnetic field geometry exactly. And so many of these things can produce similar types of changes in the pattern. I don't know if that's a satisfactory answer. I think that's the best I can do on that. I'm not sure what specific observational handle we would have on aberration in particular. I would say there are arguments about relative directions of field components and other things in analytic models, which maybe would be of interest. So there's this upcoming Narayan et al. Paper discusses that in more detail and makes arguments related to that.
Okay, one last question. In the GRMHD models, how do we handle the interaction between the electrons and the ions?
Yeah, so we don't. So basically, in the GRMHD models presented today that were done for the HD, what we are doing in calculating radiation is that we are prescribing an energy or a temperature to the electrons after the fact, and that's done in a way that is a fraction of the total fluid internal energy is chosen to go into the electrons. So this is a major uncertainty and important open issue in the field, which modifies both how total intensity images look and how polarized images look. So it's a really good question. So yeah, if you know how to do it better, please get in touch with us and tell us. I would say there's a lot of progress in this field recently in trying to map results of, say, plasma or kinetics type calculations onto physical regimes we think are of interest for a global simulation. So there's been a lot of work on both running, say, particle and cell simulations or other ways of doing kinetics calculations, and then learning those results and putting them in as subgrid models to evolve electrons in GRMHD. That is not what we're doing here, but I think that this type of information from the polarized image of the electron temperature actually will end up being a really important input. So we need to find more direct ways to get those things in contact with each other. So to understand basically if the physical processes that we think are heating electrons in these collisionless accretion flows are actually consistent with with new polarized observations. I think that's a really interesting area for future work.
Okay, with that, let's wrap up. Thank you again, Jason, for this wonderful presentation and taking the Q&A. Thank you all for attending. I just want to remind you that our last in this webinar series is going to be on April 27th, and it's going to focus on principal component analysis techniques in VLBI imaging and model comparison. So we invite you to attend that last one in the series as well. And with that, let's wrap up. Thank you.
Thank you, everyone, for coming.